Hello, welcome to another one of our Knowledge Bite clips. A vertical louver has to stop wind-driven rain. In a storm, rain doesn't fall straight down, it comes in sideways. The droplets have momentum, so even if the air changes direction, the water keeps traveling in a straight line until something makes it stop. That's why blade shape and spacing are important. A well-designed louver forces the air to turn sharply. The air can turn, but the water can't, so the droplets hit the blades instead of going through. Then the louver needs a clear path for that water to drain out again. It's interesting to note that louver performance is not intuitive. Two systems that appear visually similar may prove to perform very differently once tested. When we look at a vertical louver like the VLVF2, it seems like common sense to conclude that rain driven into the louver horizontal to the blade could make its way to the rear of the louver blade before it hits any aluminium. There are two factors that are happening at the same time that mitigate or rather counteract this hypothesis. The first is the swamping effect. Refer to an earlier video, FAQ number 9. With a vertical louver, there is no swamping effect. Water is free to drop straight down where it hits the sill tray and is directed out to the exterior. The other phenomenon that occurs with the VLVF2 is a negative suction vortex effect. You can see in the slide from CFD modeling that airflow through the louver blade creates zones where swirling air is at zero velocity while air over the tip of the blade is at 9 meters a second. These zones also create an escape path for water by slowing and drawing it down the blade to hit the sill tray and drain out to the exterior. The test certificate for the VLVF2 has the highest weather rating across the Ventuer range of louvers, maybe surprising your initial perception of vertical louver performance.